In the previous lesson, we looked at a differentiating technique that went along with natural log. So in this lesson, we're going to go ahead and learn the antiderivative or be doing some integration using the natural logarithm. And since we're going to be doing some integration, naturally we will need to do some u substitution with that since many functions do happen to contain a composition. Alright, so in the previous lesson we looked at how to differentiate natural log. Let's try to recall what that rule is really quick. So the derivative of natural log of x is equal to 1 over x for x is greater than 0. The reason for that being that the domain of natural log of x only contains positive numbers. So the antiderivative is very simple. So if I want to work backwards, the integral of 1 over x, so again that place where the power rule fails, is equal to the natural log of the absolute value of x plus c. So why do we need the absolute value? To enforce this domain restriction, because I'm not allowed to take the natural log of negative numbers. Alright, so let's just go ahead and see this rule in action. So if I want to integrate 2 divided by x, I just have this extra constant of 0, so that'll integrate to 2 natural log the absolute value of x plus c. Remember that we're doing indefinite integrals, so you do need to have your plus c at the end of these. Anytime you have anything other than just x in the denominator, that will require a u substitution. So my denominator is 4 minus x. The derivative of that is negative 1, so I'm going to have a negative out front to compensate. The integral of 1 over u would be negative natural log of u plus c. Alright, so that's how you'd use a u substitution to do that. Some of you might be to the point where you can do some of the u substituting mentally, and you would know that the answer would just be negative natural log of 4 minus, or the absolute value of 4 minus x plus c. That's up to you. But just for maybe right away at the beginning, it might be nice to practice with that again. Again, I have something other than x in the denominator. I can't rewrite this in any other way. I can't simplify it. So this is a candidate for this idea of doing 1 over u. Alright, well I have the x part of it, but I don't have the 2, so I am going to have a 1/2 out front to compensate for that. So I'm going to have 1/2 natural log, and I can go ahead, if you at this point you can handle plugging in what u is, that's great. X squared plus 1 plus c. Okay, so let's just practice with a few more examples. So if I see something like this, I can't simplify this in any way that would at all be helpful, so I'm going to try to follow with what we've been practicing with and let my denominator be 0, so u cubed plus x, or u is x cubed plus x minus, pardon me, and then the derivative of that would be 3x squared plus 1, which conveniently is what I have right there. So this is a 1 over u problem. So natural log the absolute value of x cubed plus x plus c. So even though this really didn't look like a 1 over x problem, a u substitution made this fairly easy to integrate. So let's look at another example. So let's look at some trig. So this doesn't look like a natural log problem at all, but if I were to let my denominator be tangent of x, and the derivative of tangent of x is secant squared of x, and I have a secant squared of x, that this is a 1 over u problem. So it does integrate to natural log of tangent of x plus c. So this rule can be applied to many different situations, so it should be a great tool to have in your toolbox. Okay. All right, so what if I don't actually have an integral rule for natural log, but what if, taking a look at that, I were to let my u be natural log of x? Recall that the derivative of natural log of x would be 1 over x dx. And look, I have a 1 over x, so that ends up working out really well. So this is a 1 over u problem as well. Okay, 1 over u integrates to natural log. My u is natural log of x, so I have natural log of the absolute value of natural log of x plus c. We haven't yet come up with an integral rule for tangent, and this is actually a really great application of the new rule that we learned today. So tangent can be written as a quotient, sine over cosine, or as a ratio, however you want to think of that. If I were to let u be cosine of x, just like what we've been working with today, the derivative of that would be negative sine of x. I don't have the negative, so I'm going to have to compensate for that. So it's kind of cool that the integral of tangent of x is equal to negative natural log the absolute value of cosine of x plus c. So as you can probably tell that this will be helpful for deriving some of the other trig ratios. So you need to be able to show where the integral for tangent and cotangent come from. So going through the process for cotangent is almost identical to what we just did. And the rest of the formulas here get to be a little more technical for like secant and cosecant. The derivation of those can be found if you did a simple internet search or if you chose to look through the textbook. These are two that you need to be aware of what they are. If you ever needed them for something, you could look them up. But these two integral formulas here do not need to be memorized. But remember that these two, you do need to be able to derive and show where those come from, doing a rewrite like what we did on the last example. All right, so let's just try a couple more. So let's just try to apply the secant rule. Again, you didn't need to have it memorized. It's not one that I use regularly either, so you just need to go back and look at it and see what it is. My inside function is something other than x, so this does require a u substitution. I don't have a 1/2, so I need to compensate for that by having a 2 out front. So the rule for secant was that the secant of u du integrates to natural log the absolute value of secant of u plus tangent of u plus c. Okay, so I have a 2 out front. Natural log the absolute value of secant of u, which was x over 2, plus tangent of u, which was x over 2, plus c. So sometimes for technical rules, they don't necessarily all need to be committed to memory, but you do need to be aware that the rules exist and that you are able to find where those are at so you can use them as a resource. Okay, so now I'm going to look at a definite integral. So this one has bounds, so just to do a quick refresher on that since it's been a while for you. This is going to require a u substitution. There isn't any simplification I can do ahead of time that would make this any easier. I'm going to try to let my u be the denominator. The derivative of theta minus sine of theta would be 1 minus cosine of theta, which is what I happen to have in the numerator. So this is a 1 over u du. One of the methods that I've promoted for when we do u substitution with definite integrals is to change your bounds over to u bounds. Right now these are in terms of the variable theta, so I actually want to convert them over to u bounds. Alright, so then if theta is equal to 2, if I want to convert those over to u bounds, it would be 2 minus sine of 2. Well, that's not going to be a very pretty number. We'll talk about how to deal with that here in just a minute. The lower bound, if theta were 1, if I convert that to u's, that'd be 1 minus sine of 1. Again, this is in radians. I can calculate this with my calculator, but not necessarily very pretty. I'm going to go ahead and I'm going to call this the lower bound A and the upper bound B. So how I want to do that is, that may seem like more complicated because I just got variables, but I can use my calculator to help evaluate this. So what I might mean by that is, okay, so what is 2 minus sine of 2 in radians? Well, you can write that on your page to, maybe perhaps 6 decimal places, because remember you need to be accurate to 3 at the end. But you can actually, if you'd like to refer to them as A and B, which is just fine as long as you've labeled them, your calculator can store those values for you. So we had said that we had wanted to call this B, so we hit the store button, which is right above on, and say, okay, I want to take that answer and store it as the letter B, so I hit alpha B. Now every time from now on, when I pull up B, it's going to use that value. Similarly, I want to get that other value, which I said that I wanted to store as A. You can do it all in one step if you want. Say store that as alpha A. Okay, so then when I come back, I can just use those letters to do the arithmetic for me. All right, so I go ahead and I integrate this, so I end up with natural log absolute value of u. And then my bounds are going to be from A to B. So I can do the natural log of B minus the natural log of A. So the natural log of B minus the natural log of A. And I end up getting 1.928. I often use my calculator to store values, and it's something that I highly recommend that you do as well. What might be helpful to you though is to label what you're going to store them as on here, and then from here on out you've told who's ever reading your work what you've stored them as, and you can just call them that throughout the rest of the problem. So that I would highly recommend that you do that. You can't start using different variables like A and B unless you've defined clearly what they're for. So recently we've talked about the first and the second fundamental theorem of calculus. So in this chapter we're going to be doing a lot of reviewing of our antiderivative vocabulary that we learned in the previous unit. Second fundamental theorem being one of them. Recall that the second fundamental theorem of calculus says that the derivatives and integrals are inverse operations, but we do have to worry about chain rule. So if I want to find f prime of x, that's going to be 1 over, plug in my upper bound. If my upper bound is anything other than x, I do need to run a chain rule. If I had a constant in the bottom, that would have ended up going to 0. So just 1 over x. Alright, so in this lesson we looked at how to integrate antiderivatives that are in the form of 1 over u or 1 over x using the new rule that we learned about natural logarithms.